Hello, my name is Shreyas Sharola. I am from Department of Electronics and Communication Engineering from Marwadi University. Today I am going to discuss about the combination logic circuit, binary adder and subtractor. So in the combination circuit, I have a combination circuit which have n inputs and m inputs, and there is also a one feedback path which comes from output to input. If I want to comment on combination circuit, your output should always be depends upon the input. It should not be depends upon the feedback path. So output is a function of input only. Whenever there is a change in input, output may changes after some delay. Why after some delay? Because in a combination circuit is made up of a gate, and gates have certain delay. So whenever the input changes, your output always get with much delay. You can analyze the combination logic design using the two way, where this first part, where if you looking, we have a certain inputs and certain gates in between the logics, and we have the two outputs. That means we have to find its function. It may be expressed as a boolean function or in the truth table. When it's a design procedure, you need to find what should be the logic inside this block using by given the inputs and the output. That means how many number of inputs have been given, you need to apply a different combinations and you need to make a truth table, and from that truth table you can able to design a boolean function. Let's suppose go to the first approach. You can able to design a boolean expression with analyze approach. What we had given, we had given a combination circuits and the certain inputs and a function f1. If you look at over here, this is nothing but an AND gate. So if you look what should be the function of the AND gate, it should be a dot b. Look at the second gate, we have a dot c, and the third gate we have b dot c. When you combine together, it will make a function f1, that is a dot b plus b dot c plus c dot a. Another way to design a circuit, here I have given a combination circuit. I will apply a different combinations. Let's suppose how many variables we have. I have a, I have b, and I have the c variable. So I will make a truth table with the three variables and the one function output. Let us take the first case, whenever the a, b and c are 0 0 0. Whenever the a, b and c are 0 0 0 dot 0, it always be a 0. Here a dot c, that is a 0 dot 0, it always be 0. Here also it's 0. The function, that is a 0 plus 0 plus 0, it gives me the function as a 0. So likewise, if I'll apply a different combinations, and with a different combination I'll always fill this table with the different outputs, and finally I'll get a function f1. I took the another expression like a value, that is a 1, b value, that is also 1, and the c value, that is a 0. That means the 1 1 0 combination I took, and finally I got the function f1 as a 1. So during this 1 1, I'll put the output as a 1. Likewise, I will take a different ABC variable different values, and I'll get a one function output. Based on this truth table, I'll design a K-map where I have A, B and C. That means here it will be a B bar, C bar, a B bar, C, BC and BC bar. Look at over here. Here, look at this thing like 1 and 1. Here it's a bar and A. A is a common over here, and what is the common is a C. So this will be, this is my mistake, there is not be, it should be a dot c. Look at over here, it's a b is common from this side and a is common, so this is not ac, this is a dot b, and here it's nothing but a bc. So the total function, that is a f1, I can write it's a dot b plus a dot c plus bc. This is nothing but a function. There are the two approaches. One is analyze approach, another is approach we call a design approach. Now let us discuss about the half adder. Why it's called the half adder? Because whenever you do the addition, it's nothing but addition of a one bit. I'll talk about the one bit, it's a A0. One half adder will do the operation with the one bit A0 and the B0. Output is nothing but a sum, and there is one more bit we call as a carry bit. So this is the block in which we have a logic circuit combination logic circuits, and where the inputs I have the a b, and output will be my sum and carry. So if you look at here on the truth table of far header, which is 0 0 addition with the sum and carry. Here whenever you add the 0 plus 1, sum will be 1, carry will be 0. Whenever the 1 plus 0, sum will be 1, carry will be 0. 1 plus 1, its sum is 0 and carry is 1. Okay, now look at all the, whenever if you want to design a boolean expression, look at the sum. This is the two possibilities where I am getting the 1. So I can write the sum as a bar b. A bar, the reason is a is 0 plus a b bar. This is nothing but a XOR b. Look at the carry. What is the possibility of the carry we have here? Now look at the a and b. Where are the 1? That's why I can write as a dot b. So this is a boolean expression for the sum and carry. If I want to design a combination logics over here, this will be my combination logic, where a and b is nothing but XOR gate, and the a dot b is nothing but an AND gate will go to the carry. This is nothing but a half header. When we talk about the full header, there are the three inputs we have. Why we require the first of all the, let us talk about the full header. When we talk about the full header, why we require the full header? Why we cannot able to use the half header? The reason not to use the half header, sometimes the reason is that suppose I want to add this another 2 bits addition, that is a1 a b1. When I do the addition a0 b0, my sum will be s0 and the carry will be over here for the previous carry. Now if I use a half header, I can able to do the addition of the two inputs, either a1 b1 or carry a1. But if I need a correct answer, I need to add these two things, the carry a1 b1, and then I will get a correct sum and also the carry. That's the reason we are going to a full header, where the full header we have the three inputs like a, b and the carry. Then I will get a sum and also one carry. Now look at over here, there's a full header block which have the input a, b, c, y, that is the input carry, and the output is sum and carry out. Here look at, take this example. When I do this operation, the 1 plus 0, its sum is 1, carry is 0. When do the addition of sum with 0, it's 0 and 1. So this one is carry, this one is summation. Whenever you do like 1 plus 1 is 0 and the carry is 1. When you again do the addition, it's give me the 1 and 1. That means sum is also 1 and carry is also 1. Because you can able to make the truth table. Then finally come with the K-map. Here, based on this, if you look over here, this is nothing but a, here, this is a one combination is possible, another combination, and this combination. It gives me AB plus BCY plus ACY. Look at the combination of sum here. If you look at the sum K-map, there is no parallel possible because each ones are separate. So if you make for this, it's nothing but a here. If you look at over here, 0 0, that is a B bar CY bar. So this is nothing but expression. Same way we can write for this and this and this. This finally, what you can write here, if you take out the common here, CY bar, what it will be, A B bar plus A bar B plus, if I take the common, this is a CY. CY is a common, it's A bar B bar plus AB. Here, now this one is a CY bar. What about this? It's nothing but a AXOR B plus, I can write CY. Here I can write AXOR B is X not D. So again, it's a, if you take the X, the CY bar X plus CY X bar, again it's a AXOR B XOR CY. So what we have over here, it's nothing but a XOR gate and AND gate and OR gate. Just nothing but a full adder. Like How we can able to design a full adder using the two half adder? You know about half adder here, A XOR B XOR C. That means here the output will be A XOR B and another input will come from a C. The final sum will be A XOR B XOR C. Same way we can also be able to design a carry, because same way you will get a carry also. So this is nothing but a full adder using two half adder. Now let's talk about the binary adder. Here, whenever if you do the operation of 4-bit binary adder, let's say x0, y0, when you do last, there will be the answer, that is S0, S1, S2 and S3, and finally that will be a carry out. So here there are the two numbers x0, x1, x2, x3, y0, y1, y2, y3, and you addition, this is the input carry you have. Okay, what is the output you will get? I will get a 4 sums and 1 carry as output. Now here, how the carry has been forwarded. Now look at, we need to use the full adder. The reason is I have to use x0 plus y0 plus the input carry. What is the output? I'll get a sum. The carry will be forwarded to the next block. This is C1. That means you are doing the addition of x1, y1, c1, and finally you will get answer as a S1, and the carry again will be forwarded to the next block. The carry will be propagated to the last block, and finally I will get C4 as a carry out in this block. Here the binary adder, the reason we never use the binary adder due to this propagation delay. That means till the last carry comes, we need to wait. Each block need to wait to the previous carry. That means this block is wait to get this previous carry, again this previous carry, and finally we'll get the output. So there is always be a propagation delay to get the output. When you talk about the half subtractor, it's simple subtractions what we are doing, but instead of sums and carry, we'll get a difference and borrow. A minus B, that means whenever you subtract the two numbers A minus B, you will get a difference, and the remaining will be a borrow. This is the block diagram of a half adder. I have the two inputs A, B, and I'll get output as a difference and borrow. Truth table if you make, let's suppose here, the 0 minus 0, the difference is 0, borrow is 1. 0 minus 1, borrow is also 1, difference is 0. 1 minus 0, difference is 0, borrow is 1 minus 0, difference is 1, borrow is 0. 1 minus 1 is 0 and borrow is 0. When you write the difference here, like this is the 1 and this is the 1, again it's a 0 and 1, so I can write A bar B plus A B bar is nothing but a XOR gate. What about the borrow? Look at this thing, it's a bar and B, so A bar and B. This is nothing but a boolean expression for difference and borrow. Same way you can also able to design a circuit based on the boolean expression obtained from the truth table. When we talk about the full subtractor, it's not a adder, it's a subtractor, it's by mistake. So it same like A minus B minus C, that is a carry, that is a will often there are three inputs A, B and C. You will get a output as a difference and borrow. This is a truth table for the full subtractor. Here take in any case, let's suppose this take case the 1 minus 0, what is the output? Again the difference is 0, borrow is 0, minus 0, that means the difference is 1, borrow is 0, the difference is 1, borrow is 0. Let's talk about the 1 minus 1, 1 minus 1, difference is 0, borrow is 1, again the 0 minus 1 is not possible, so you need to take a 1 borrow, that is a 1 0, 1 0 minus 1, it's a 1, and you have a borrow 1, so difference and borrow both are 1. So you will make the K maps, you will get two boolean equations for two different things, same what we had done for the sum and carry is a difference and the borrow, and try to implement using a combination logic block. So we have a three inputs A, B, C, Y, the difference and borrow. Inside this we have a combination logic. It's a full subtractor using two half subtractors. Same thing, when you combine the two half subtractors, you will get the combinations of a block. And this is nothing but a full subtractor. If you don't want to use the full subtractor, you also can able to implement a subtraction using the adder block. How? Let us take about the example. Here, you know about this a minus b. If I want to do the subtraction, I need to subtract b from a. But I can write a plus minus b also. Now, this minus b I can write as a 2's complement of a b here. This is the 1's complement plus 1. It will give me the 2's complement of b. If I look to the diagram, if I implement a plus b bar plus 1, it's give me the same operation as a minus b. Now take the example of an adder. Now here, I have 4 some carry. I need to do the addition of a0, a1, a2, a3. Here I have b0, b1, b2, b3. But what I need a b3 bar, b2 bar, b1 bar and b0 bar. It is possible if by putting the NOT gate. That means I will add a plus b bar, and from where the 1 will come, this carry will give me the 1 from over here. So it's give me the a plus b bar plus 1, which is nothing but an operation of a minus b. Again I will get a sum and carry. So this is how also you can able to implement the binary subtractor logic. Now here, if you want to use a binary adder and subtractor as a universal circuit, that means there should be one switch which gives me when this is a 0, let's suppose 0. You know about the XOR gate. I have the two inputs a, b, y, a 0, 0, a 0, 1, 1, 0, 1, 1. So 0, 1, 1, a 0. This is nothing but a truth table of an XOR gate. Now look at over here. So instead of this, I'll take, now instead of this a, let me take the switch M. Now look at over here. When M is 0, I will get the same B at the output side. That means B is 0, I'll get output as 0. If B is 1, output I'll get a 1. Now look at over here. When M is 1, if B is 0, output will be the complement of B. If B is 1, output will be the complement of B. That means here, when M is 0, I will get the output as the same as a B, but when M is 1, I will get output as the same as a B bar. So here, the M works as a switch. So I will use XOR gate. So if M is 0, that means Y0. That means here, it will be same as a, here I will get Y0, Y1, Y2 and Y3. It will do the addition of A, X and Y. I'll get, it work as an adder. But if my M is 1, that means here, if instead of this, if it is M is 1, that means what I will get Y0 dash, Y1 dash, Y2 dash, Y3 dash. That is a complement of Y number. Now where should be the one addition? This one will be added over here. So it will be worked as a, if it is worked as a X plus Y bar plus 1, and that is nothing but a X minus Y. That is a subtraction. So M is a switch which depends, will give you the function as addition or subtraction. Thank you for watching this video. If you have any query or any questions, mail me on my mail ID like shreyas.charola@marwadieducation.edu.in. Thank you. Have a nice day.